Hello and welcome to our first lesson of the very last unit of calculus and vectors. We are looking at lines and planes, which is an extension from vectors. So before we begin, we're going to start with our learning goals. So we are going to represent and analyze lines in 2 and 3 dimensions using vector and parametric equations. So I will say also this unit has a lot of new information as well. Every lesson is going to be pretty heavy with the amount of content covered, but it is a relatively easier concept to pick up on, especially after you've had a lot of practice with vectors. So let's get started. So first we are looking and comparing lines and vectors, which is pretty much what we have already seen. So with lines, lines are bidirectional, which means that they go in both directions. Keep in mind that's a straight line. Um, in vectors, however, vectors are unidirectional, right? So they typically go in one direction. They have a tail, which is the starting point, and the head, which tells us which direction it's going. Now, with lines as well, a line segment has a finite length, which means we know what the length is. But a line is infinite in both directions. So that's how we represent a line with the two arrows. A line segment, however, would be, there we go, that's my straight line there, have two dots at each point, which tells us the endpoints, and from that we can determine the length. Vectors also have a finite magnitude. Remember, vectors, a big part of what they're known for is having a magnitude and a direction. So it is known what the magnitude of our vector is. Lines also have a definite location, whereas vectors have no fixed location in space. And two lines with the same direction and location are the same and are said to be coincident. And I will define this for you later on in context as well, but that's pretty much two lines that are exactly the same. Whereas two vectors with the same direction and magnitude are the same and we call them equal. So they may not necessarily be in the same space, right? We could have this vector with this length and I can copy this vector over down here. And these two vectors still have the same direction and magnitude, but they are not coincident. They do not overlap, but we could translate one to move it in space, so for them to be coincident then. But on their own, we say these two are just equal vectors. So vectors are also, they have the direction. So now when we are connecting vectors to lines, we have a new definition here, which is a direction vector, which tells us which direction a vector is going. So it is a non-zero vector, and it is used with the letter M. And we also have a coordinate here, A, B. So right now we're starting in R2. So that's why we only have the X and Y component, and then we'll add on R cubed in there as well. So it's a non-zero vector M that is parallel or collinear to a given line. So it has a tail at the origin and its head is at point AB, which again tells us which direction it is going in. Now, direction numbers are the X and Y component of the direction vector, right? So how much in the horizontal space are we moving and how much in the vertical, which is our Y. So let's do an example. We have a line that passes through the point A, which is half and -3, and point B, which is 3/4 and a half. So determine the direction vector for this line and write it using integer components. So this part is just a review from vectors. So given 2 points, the vector that connects them is given by the difference of the x components and the difference of the y components. So 3/4 minus half, and then half minus -3, which gives us 1/4 and 7/2. But this is a rational no, we have rational numbers here as our direction numbers, and we were told to use integer components. And so remember, with vectors, we can find scalar multiples. So I multiplied by 4 to get 1 here, and multiplying by 4 here will give us 14. So our direction vector will be given by vector m, which is 1 and 14. Now, here we're going to connect it to the graph as well. So a line passes through point 2, -1, and has a direction vector m, which is given by 5, 2. So sketch this line. So first, let's look at the direction vector, which is this red line here. So 5 is our x component, 2 is our y component. So we have our tail at the origin and our head at 0.52, and this is the direction vector. And connecting it to linear lines, this is also has a slope of 2/5, which is our rise over run. Now, a line that is parallel to this and goes through point 2, -1, it can be shown with this blue line. So as you can see, these two are parallel, and this blue line is going through the point 2, -1. Now, again, we can make connections with linear lines. This, you have a point, you have the slope, and you can find the equation of the line. But now working with vectors, we're going to be representing this a little bit differently. So you've seen the sketch here, and now I'm going to give you the definition for how we write the equation of this line using vectors. So we have two forms that we're starting off with, which is our vector and parametric equation of a line in R squared. So let R0, the vector, be a vector from the origin to point x0, y0. So this is a point on our line, and it's given to us, similar to point 2, -1 that was given to us here. M is a direction vector with components A, B, and remember this is your x and y component. And t is now going to be an unknown parameter for us, and t will be in the set of real numbers. So then the vector equation, which is given by r, is equal to r0, which think of r0 as a starting point for us on the line, and plus t times m. So that direction vector, and now any scalar multiple of that direction vector. So with the line we had above, r would be defined as, our point here is 2, -1, plus a parameter t, and really you can use any parameter here. You'll often see s and t used, but you can use any other variable too. And our direction vector was 5, 2. And we do also have to add that t is a real number. So this is now the vector equation of that blue line there. And again, remember, we're interpreting it. This is one of the points, a given point on the line, and this is the direction vector. And any scalar multiple of the direction vector from this point will give us other points on this blue line. Now, the parametric equation pretty much comes from the vector equation. So consider that R really is just giving us x and y. But x and y is now any point on this blue line. So if we want to find out what x is, we would take 2, which is x0. So this is x0, y0, and this is m here. And really, this is also r0. So x would be 2 plus 5t. So if you take that starting point, the x component of the starting point, which is 2, and then add the x component of the direction vector, which would be 5 times t with that scalar multiple, then you get any x value. And the corresponding y component of that x is -1, which is y0. And now this is plus 2 times t. And again, t in the set of real numbers. And so if I wanted to find any point on this line, I can either input values for t and find the x and y, or if sometimes you'll be given the x and y and asked to find what parameter gives that specific x and y. So let's look at this example here, which gets us to test that out. So for the line in question 2, which is this equation that we just found, and let me maybe just, I'm going to box it for us. to know that that's what we're using. We're asked to determine whether points P and Q are points on this line. And we're going to start with point P, which is 27 and 9. So this is really setting up this parametric equation, and then you have two equations, one variable, and you're trying to solve. So if P is a point on the line, then there would be a parameter T in the set of real numbers that would satisfy these two equations. So that means we will have 27 equal to 2 plus 5t, and we will also have 9, which is y, equal to negative 1 plus 2t. That's exactly what I have here. Now, from this first equation, you solve it and you get that t is equal to 5. And now, we're not really, you could try solving this again, but you can just try through substitution now. So I will substitute t equals 5 into my second equation and see that I get 9, which is exactly what I wanted. So then there does exist one constant parameter, which is t equals 5, that satisfies this parametric equation to give us the point 27, 9. So then, yes, this point is on the line. Now, with point Q, we similarly want a parameter t so that we have 2 plus 5t equals to 32, and now negative 1 plus 2t equals to negative 1. So solving the first equation, we have t equals 6, but now, through substitution, negative 1 plus 2 times 6 gives us 11 here. So the y component based on t is equal to 6 would be 11 and not negative 11 like we were given. So the point Q does not satisfy the parametric equation, and we can conclude that it does not lie on the line because there isn't one constant parameter t that will satisfy both of these equations up here. Now, example 4, we're asked to determine the vector and parametric equation of a line passing through points A or point A with direction vector m, which is equal to negative 3, 3. So this is really simple now. We're just setting up using the definition above. So x0, y0 is that point A, which was negative 1 and 2. And now we consider OP, which O is the origin, which gives us R0, which is that starting point that we have, and it's negative 1, 2, or the direction vector that we have. It's our reference point. So it's the point that we're starting with, and then the direction vector is actually m, and this is negative 3 and 3. So just using the formula above, the vector equation given by r is going to be that first point, negative 1, 2, plus, and here I've just picked t. Again, you can pick s or any other variable. So t times negative 3, 3, with t in the set of real numbers. And now the parametric equation, again, we get from here. So the x values, which is negative 1 minus 3t, and the y is going to be 2 plus 3t. And you definitely want to pay attention here to both your parameter here and then the values of your direction numbers in order to set this up correctly. And we do also, whenever we're writing the parametric equation, we do add that t is in the set of real numbers here as well because we are also using the variable t here. Now for this equation, we're asked, what are the coordinates of the point where the line crosses the x-axis? So similar to how we work with lines, at the point where the line is crossing the x-axis, we have a coordinate that would look like a0. So our y component is still going to be equal to 0. That being said, our y component here is given by 2 plus 3t. So we let this parameter equal 0 to get t equals negative 2 over 3. Now we solve for our x based on this equation here, negative 1 minus 3t, and we get x is equal to 1. So the coordinate of the point where the line crosses the x-axis is 1, 0. Now, question 5, we have the vector equation for a line, and we're asked to determine the vector equation for the line perpendicular to that line. And we're also told the point that it passes through as well. So first we let vector M, be the direction vector of the perpendicular line. So um, we want to find the vector or the direction vector, and we also have the reference point here that will help us set up the vector equation. Now, to find what M is, we have to use our knowledge of dot product, which told us that um, the dot product of this vector with the direction vector of the other line, so the dot product of the two direction vectors will be 0 when these two lines are perpendicular. Now, in other words, we are just using the dot product of the algebraic vectors here. So this will give us negative 3a plus 2b is equal to 0. So now we have a setup for the direction vector of that second line. Now here, you can pretty much pick any a and b that would satisfy this equation. And the simplest solution we have here is to pick a is equal to 2 and b is equal to 3 because this is already negative. So together we will get that negative 3 times 2 plus 2 times 3 is going to give us 0. So the direction vector is 2, 3. And so the vector equation of the perpendicular line is given by, so this is 6, 5 is the reference point. So the point that passes a given point on the line or the point that the perpendicular line passes through. And this is now that new direction vector, M. And we have a parameter t here. So see how here we had s, and now here we have t, and we say that t is in the set of real numbers. And now I'm going to make a connection to our linear lines. So if you remember, linear lines in y-intercept form are given by y equals mx plus b. And the reason for that is because your y-intercept is given right there by b. We also had the Cartesian or scalar equation of a line, which we also get from here. And it's pretty much you move all the variables to one side and you multiply through, for example, if you had y equals half of x plus 3, you move everything over to get y minus half of x minus 3 is equal to 0 and multiply it through by 2 to get integer coefficients. So then we have 2y minus x minus 6 is equal to 0. And that is your Cartesian equation of a line. And a here would be 2, b is negative 1, and c is just negative 6. Now, connecting this back to what we've been working with, so if a line segment AB has the slope m, and remember, we've used also m before for slope, and we're making a connection between that m to the direction vector m, which has just the arrow on top. So if we have a slope b over a, which is rise over run, and remember, b corresponds to the y component. So it is the change in y over the change in a, and this is parallel to the vector m, which is AB. So here we have this line segment, and its slope is given by b over a because it has a rise of b and a run of a. Now, if I just move this over to have it start at the origin and now it's a vector, then this is really also a change in y of b and a change in x of a, but now because we start at the origin, we have a vector, which is our direction vector m, and it is equal to a, b written in component form like this. So then any a, b in the set of real numbers gives us the direction vector and the slope, and the only exception to that is when a is equal to 0. And what happens when a is equal to 0? That just means that we don't have any runs, so we're only rising. So this is a vertical line, so you're only going up. You do not have any horizontal movement. And that was also we saw with when we learned linear functions as well. It's not even considered a function for us because it did not pass the vertical line test. So another connection there as well. And I do want to take a moment here to go back to this one and make this connection for you. Because here, with this first line where we have m is negative 3, 2, then we can say the slope of this is 2 over negative 3. Now, if you remember, the perpendicular slope here is the negative reciprocal. So it's 3 over 2. But now this is exactly here. This is y over x of this direction vector that we found here. So both from the dot product and based on what we know about perpendicular slopes, we were able to get that 2, 3 value. Now let's look at another example. Here we have the line, and again, this is y-intercept form. Y equals 3 over 5x plus 4. So our slope here is 3 over 5. And we're asked to determine the vector and parametric equations. So one point, and it's our simplest point that we can find, is the y-intercept, which is 0.04. So we know the line for sure passes through this point. And now the slope, we have 3 over 5. So remember, this is the y, this is the x. So one minor correction here. This should be swapped. This should be 5, 3, and then same here. This should be 5, 3, because remember, it's y over x. So then when we write it this way, we have xy. So we have to follow this order here. So then the vector equation is going to be r, which is given the vector r, which is equal to our reference point 0, 4, plus parameter t times the direction vector, which is 5, 3. And t is in the set of real numbers. And now I have to fix this one as well, because this is actually going to be 0 plus 5t now. And then y is going to be 4 plus 3t. And again, we have t is in the set of real numbers here. Now, for the line given by the equation r, which is equal to 1, negative 4, plus s, negative 3, negative 6. So this is our direction vector with s in the set of real numbers. Now we want to find the equivalent equation in Cartesian form. So remember, it's that ax plus by plus c is equal to 0. So we have the direction vector here, which is m, given by negative 3, negative 6. So then the slope is going to be y over x, which is negative 6 over negative 3, and this is equal to 2. Now, we also know that the line passes through the point 1, negative 4. So this is really just going back to linear equations, and we're trying to find the y-intercept. So we use y equals mx plus b with this point and the slope. So we get negative 4 is equal to 2 times 1 plus b. And we find that b is equal to negative 6. So in slope y-intercept form, our equation is y equals 2x minus 6. And now rearranging this, I will end up with 2x minus y minus 6 is equal to 0. So just generalizing that as well, and making now a new connection to it with the Cartesian equation of a line in R squared. So given the equation ax plus by plus c is equal to 0, the normal, remember normal is perpendicular to this line, is given by n and vector n, and this is actually just a and b. And the normal is drawn from the origin to the point n, again given by a and b, and this will be perpendicular to the given line. Now, from there, and I'll use my diagrams here for this, if we have two lines, L1 and L2, so we have L1 and L2 here, and they have normals that are vector n1 and n2, then these two lines are said to be parallel if and only if their normals are scalar multiples. So that is vector n1 is equal to k times vector n2 for k in the set of real numbers, and k cannot be equal to 0 or else we just get the 0 vector. So from here, we can also conclude that their direction vectors will also be scalar multiples. And of course, looking at the diagram as well, that makes sense. If these two lines are parallel, L1 and L2, then consider their normals, which is N1 and N2 drawn here. which form or which are perpendicular to those lines, then these two, it's clear to see, are parallel direction vectors as well. And so the direction vectors for L1 and L2 are also parallel here too. Now, we also say that these two lines are perpendicular if and only if the dot product of their normals is 0. So consider here, and not the best visually shown, but here if we have L1 and L2 and these are perpendicular, then the normal to L2 and the normal to L1 are given here, then these two will have a dot product that is equal to 0. And again, because we're working with vectors, we can easily find that using the product of their components and then adding them all together. And so we can also conclude that the direction vectors will also have a dot product of 0. And the reason why we include this as well is because you're actually going to work with this whether your equations are given in vector equation, which you will be using the direction vectors themselves, or if they're given in Cartesian equation, in which you will be using their normals based on ax plus by plus c is equal to 0. So given these two lines here, L1 and L2, we are asked to show they are parallel and non-coincident. So from above, we know that the normal of L1 is given by 3, 4, which is A and, or sorry, A, there we go, should be -4 and this should be -8. And N2 is 6, -8. And these two are scalar multiples, so based on the definition above, and remember, because it's if and only if, we can use it this way as well. Because these two are scalar multiples, we can conclude that the two lines are parallel. And additionally, because it is a scalar multiple that is not equal to 1, then, so we are multiplying by 2 to get the other one, then they are also non-coincident. So for them to be coincident means that these two would have to be equal. And in that case, we could also see that there does not exist a t that if you multiply this complete first equation, you would get the second equation. And that's also our definition for coincident lines using their Cartesian equation. If they are coincident, then their equations are also scalar multiples of one another. So considering L1, for example, I could give you L3, which is 9x minus 12y minus 18, which is equal to 0. And this is really 3 times 3x minus 4y minus 6 equal to 0. But this was really L1. So then we can say L3 and L1 are coincident lines, but L2, because this value is different, then they're just simply parallel because they have the same direction vector. Now, extending this to R cubed, and it's very similar. We just have that Z0 in there because we have the Z component. So we let the reference point be the point x0, y0, z0, and this is the point from the origin, or the vector from the origin to the point x0, y0, z0. And m is the direction vector, and it now has that c component, so a, b, c. And we also still have t is the parameter. So with the vector equation, same thing, r0 plus t times m. And now with the parametric equation, which we derive from the vector equation, we have the same process, except now we also have z, which is equal to z0 plus t times c, again for t in the set of real numbers. So let's look at this example here. We're asked to find the vector and parametric equation of the line passing through points A and B. So the first thing we do is find the direction vector M. And here I chose to do B A. You can also do A B, doesn't matter. So here we are we're subtracting the components of B from A, and we end up with the direction vector -5, -4, 6. Now, the vector equation will be, and here you can choose either A or B as one of your reference points. It really doesn't matter. and it's going to be plus S, and here is my direction vector here, M. And so just to confirm, yes, I use point A here. So the reason also why we choose point A here has to do with this vector equation that we used here as well. So then from this vector equation, I can derive the parametric equation. So x, y, and z. So x is equal to 2 minus 5s, y is equal to -1, and it's minus 4s, and, or sorry, it should just be, oh, it should be plus minus 4s, which should give us -1 minus 4s. And then z is 4 plus 6s. And there we have our three equations. And so could we have used the direction vector m, which is AB, which would give us 5, 4, -6 to get the same result? And yes, pretty much yes, you can. Because consider that t is a parameter in the set of real numbers, then if you are using -5, -4, and 6, then this is the same values. You might just have different parameters of t for your equation, but your direction vector will be the same. You will, or at least it will work the same in terms of the line and getting from one point to another point on the line. So pretty much, yes, these two direction vectors would be interchangeable because you have scalar multiple that can account for that difference in the negative of the components here. So if you have -5 versus 5, you can easily fix that with the t and make the same answer. And our final key information for this lesson is symmetric equations of a line in R cubed. And this will also work with R squared as well. You will just have the z component, so seeing it for R cubed, you'll be able to use it for R squared as well. But what you do here, or what the symmetric equation is, you are taking the difference from any general point. So let's say we have a point P given by X, Y, Z on our line, and you take away the values or the components of the reference form or the reference vector, and you divide it by ABC, which is the direction vector there. And I'll show you briefly how we come to this equation here. So consider your uh, parametric equation. So we have x0 plus ta, y0 plus tb, and z0 plus tc. Then, and we also have t is in the set of real numbers. So we know for any given point, P, which is x, y, z, t is a constant here. So then if I start by finding t here in the first one, then what I'm really doing is x minus x0, take away, and then divided by a. Same with here. I have y minus y0 divided by b, and t here is z minus z0 divided by, oh, sorry, c. And so, as you can see, these are exactly the symmetric equations that we are seeing here. And it's pretty much all of these are, and maybe I'll add this part in for you, but this is equal to, they're all equal to t. And you will see sometimes this equation will help us, but you should really be comfortable with changing forms from vector equation to parametric equation to Cartesian equation, and now the symmetric equation of a line. The only exception with symmetric equations is that A, B, and C cannot be 0, and we'll actually see some special cases of it, but generally when you have this case, we won't be able to use the symmetric equation for those specific components. So, for example, here we have the symmetric equation. We want the symmetric equation of a line passing through points P and Q. So again, we find the direction vector, which is given by M, and M, we're finding the difference of the x, y, and z components, and we get -6, 0, 6. Again, because we can use any scalar multiple of the direction vector, which I hope you learned from this question here. Pretty much any scalar multiple works as well. So then I have chosen to use 1, 0, -1 because I can divide by 6 here. And so here I'm already showing you the case where B is, so this is A, B, C, B is equal to 0. And so we actually are able to use the symmetric equation, but just not for the y component. So you would just write x, um, and I've chosen point P as my reference point here. You can do Q as well, same thing. So here we have x minus -2, which is x plus 2, and A was 1, so divided by 1. And here we have z minus 1 from here, from the point P, and divided by -1, which is C. And what I've done here is y is equal to 3. And what does it mean for y to be equal to 3 here? So consider that y is 3 here, and y is 3 here as well. So what this means for us is y stays fixed at 3. That means the parameter t does not actually impact the component t. So in our direction vector, we saw it show as 0, and now in the symmetric equation, we just have y is equal to 3, and we're not subtracting, or sorry, we're not dividing by any component here, especially because b is 0. And again, this just means that any point on this line will have a y value of 3. And that's what y stays at fixed means there for us. And that was the last example of our lesson. So you have some practice questions here that you can work on, and additional work posted for you on Google Classroom. I have also included some simulations for you to be able to explore vector equation of a line and how the different parameters impact the shape. So please get comfortable with what the geometric interpretations of these lines are. And that was it for us today. As always, don't hesitate to reach out if you have any questions, and I will see you all next class.